If you stand up and sit down at the stadium very quickly, it won't help make the wave go faster. What would make the wave go faster is if your neighbor's reaction time was shorter. If your neighbors has to react to you more quickly, they have to be more tightly coupled. If you want the slinky wave to go faster, what you do is you tighten the slinky, you pull, you stretch it out. Now all of the pieces of metals are under more tension, and when you jerk one piece, now those little pushes will travel more quickly. We also saw this with light. Mr. Maxwell proved that no matter how you jiggle the electric charge, the traveling electromagnetic wave always travels at the speed of light. In this case, there are no material objects involved, so there is no mechanism to speed up the speed of the light. We are stuck. It is what it is, and you cannot make it go any faster. Waves are very closely related to this oscillatory motion of the medium. The one is really part of the other, and physicists love to look at this kind of simple oscillations. We call it simple harmonic motion. Simple because it's just something going back and forth, and harmonic because that makes us think about the music and musical strings, something that just moves in a nice, simple back and forth patterns. The mathematics of the simple harmonic motion is described by a mathematical function called the sine function, or the sine wave. If you were to make some graph of the sideways position of the spot of water, or spot of the slinky, or the one of the people in the stadium, I really need a continuous wave. I need to keep wiggling the end of the slinky. I need to have a whole bunch of the waves going by. In the stadium, we don't usually do that, but you could imagine somebody rises up and sit down, then they rise up, then they sit down. Now you have more like a water wave and continuous wave. Now, if you plotted the position of anyone individual piece of medium and you charted it on a graph, you would see it goes up and down in a nice, smooth sine wave. Simple harmonic motion is a name that we give for this ideal oscillatory motion, and you might ask, well, are real things behaving in this ideal way? The answer is it's a darn good approximation in a huge number of circumstances. It's remarkable how many things have motion that is practically indistinguishable from simple harmonic motion. The slinky is a pretty darn good simple harmonic motion for the individual pieces. The water waves work really well until you go right next to the beach. In the electromagnetic waves, it's truly ideal. Electromagnetic waves are a perfect wave and motion. If you graph the strength of the electric field at some point, it would be this beautiful sinusoidal wave. What makes such a motion? Why is it that so common? Anytime any material object has a place where it belongs, and where it has an equilibrium point, and you disturb it, and it is pulled back and there, no matter which way you disturb it, and it is pulled back home, and that's going to make simple harmonic motion. Wow! Again, what makes such a motion? Why is it that it's so common? Anytime any material object has a place where it belongs, where it has an equilibrium point, and you disturb it and it is pulled back there, no matter which way you disturb, it is pulled back home, and that's going to make simple harmonic motion. Wow! So it's a disturbance of equilibrium, right? And the phenomena of simple sinusoidal wave is the phenomena that they going back to the most stable state, which is equilibrium. It's the guitar strings that you pull away from equilibrium. There is now tension in the strings that are trying to restore every piece of metal back to that flat position. Of course, you've been pulled all the way, and now they are moving. Inertia keeps them going, and an object in motion remains in motion. That's a rule for little piece of metal. They are all connected one to the other, but each one of them is obeying Newton's law. They keep on going and they go past the equilibrium position, but as soon as they go past, they are being pulled backward. Wow! They are pulled forward and then they are pulled backward. Then they are pulled forward, then they are pulled backward, and it goes over and over again. If there is no damping, if there is no friction in the leveling of these metal molecules, one with the other, the metal atoms, then this will keep on going for an arbitrarily long period of time. This oscillation can keep on going. Wow. Ideal simple harmonic motion never stops. In real life, it tends to fade away in amplitude if there is a friction involved. Right. A pendulum would do the same things. You lift it up and it is pulled back down to the origin, and then it has some inertia and swings on the through. You can start to think about all sorts of circumstances in the life, atoms in any crystal microscopically. If you pull them aside, all of the rest of the crystal is sitting there, and so they are pushed back to the spot where they are as far away from everybody as they can be. Of course, they will overshoot, so they also undergo simple harmonic oscillation. Wow, so cool. You will have a wave anytime you have a simple harmonic motion, and one object that is coupled in some way to another object that can do exactly the same thing. These two things in the nature, simple harmonic motion or oscillations, and waves just come together, and we see it all the time. If you moved and your neighbor moves, that's all you need to make wave start. You can think about all sorts of physical situations where this might happen. And in this next lecture, we are going to talk about some situation where it happens where it's not so completely obvious. Wow. I want in this lecture to think carefully about how we would know for sure that we have a wave happening. When you have a wave, you can look deep or you can step back. If you zoom in, what you see is motion of the medium, and it is simple harmonic motion. If you step back, you see the traveling wave with some speed, and you no longer think about medium. You no longer pay any attention to the medium. You just notice the disturbance itself, and all of a sudden, it feels really different. It doesn't feel like a simple harmonic motion. I'm watching this little blip at the top of the particular wave crest, and it seems to be moving in a straight line like a particle. You can see how this particle-like aspect is there in the collective motion. Wow. What is it about wave that's particularly unique? Well, so what is it about wave that's particularly unique? Well, I would argue that one of the most remarkable things, one of the most spectacular things about the fact that it isn't particle is what's happening when two waves come together. Let's start by thinking about the Slinky, because that's a nice, clean example. You don't have to worry about things spreading out in multiple dimensions. A Slinky is a one-dimensional wave. It's just a pulse that travels down a nice, beautiful, straight line. Imagine this long Slinky, and you're at the one end, and you make a blip, a pulse. It starts traveling, let's say, from right to left, and I'm at the other end, and I make a blip, and that makes a pulse that's going the other way. We have these two pulses, and they're heading towards one another. At first, they can't possibly know about one another. the blip over here and the blip over there have no mechanism yet to communicate. But as they get closer and closer together, you realize that at a certain point, they are going to touch. There is going to be some kind of interaction. And what is that interaction? Yes. Well, once again, this is a question for experiment. You can imagine what might happen. You can imagine lots of things. If you are thinking like a Newton, you are thinking that these are particles, and you might imagine that they will bounce one off of the other. The incoming pulse will turn around, and the other incoming pulse will turn around. That's not at all what happens. So you have to watch carefully. What you see is they just pass right on through one another, and after they have passed by, there is no sign of the interaction. Yes. This is a property of the waves. You never see what was happening before. Just looking at this one point, at the one point, you never see, you never know, right? Because there is no trajectory, there is no pathway, there is no footprint you can see. They just slipped right through one another. That's a spectacular, not a particle-like. Particle coming together head-on will clash. They will either stop or they'll break, or they'll go flying in some other direction. But whatever it is that particles do, they are definitely not just passing through one another. You might be wondering how I know that they pass through one another. Maybe they bounced. I mean, after all, I see a blip coming in and I see a blip going out. How do I know which is which? Well, think about the experiment. You could convince yourself quickly. When you make your blip, make your twice as big as mine, so you have a doubly big pulse coming in the way, in the one way. I have a singly big pulse coming in the other way, and they pass through one another. The little one just keeps on going, and the big one just keeps on going. It's clear as day, so you can really convince yourself that this is the way waves behave. Now comes the most interesting part of the wave behavior. This is a part that is the most distinguishing characteristic of the wave, that is very, very different from particles. Even more than the passing through the one another is what happens at the moment when they pass by one another, not afterwards, but at the moment of the interaction. We have some fancy names for this. I've often been using the word superposition. When you have two separate motion or two separate things, like two forces or two fields, and they happen to both be at the same place at the same time, they add up, so summation. Waves superpose in this way also. If you send in a 1 centimeter tall up wave and I send in a 1 centimeter tall up wave, at the moment, at the place and time where they pass through one another, if you take a snapshot, what will you see? Well, you'll see the slinky, and the slinky has to be somewhere at every point. It has to be located somewhere, and you'll see the peak of the slinky is 2 centimeters tall. Wow! The blips have added, and 1 plus 1 is 2. What would happen if I added an up pulse coming from one direction to the down pulse coming from the other direction? You can jerk the slinky either way. You don't have to make a full oscillation of your hand. You can just make a little jerk down and back. Start at the equilibrium, and that makes a little blip that just goes down on the one side and just goes up on the other side. These two pulses are coming towards one another. After they pass through the one another, we know what's going to happen. They are just going to keep on going. Yes, as if there is nothing happened. the up one keeps on going, but what happens at the moment of the interaction? If you take a snapshot, what happens when you add positive and negative? You have 0. It's quite impressive. It is as if the wave just disappeared for instant in time. If you took a snapshot, you'd see the completely flat Slinky. Now, that might seem paradoxical. Have we lost conservation of energy here? I mean, the waves are carrying some energy and some information. Oh, it's still there. It's like taking the snapshot of the pendulum that just happens to be passing through the origin. If you took the picture, you'd say, oh, it appears to be at its equilibrium-less position, and it is the equilibrium-less position. But the pendulum is still moving. The Slinky is really still moving. Parts of the Slinky are moving down, parts of the Slinky are moving up. You just happen to catch them at the lovely moment where the two waves interfered with one another and apparently cancelled one another out. The superposition is one name that we give to this adding up of the waves. Interference is another name that we give. I don't know if I like the word interference as much, although everybody uses it, because interference makes me think that afterwards they will be different, that they interfered with one another. Interference makes me think of the things that are being stopped, but it's just a word, and what it means is superposition. Yes. You can have a constructive interference, which is the two up pushes adding up to a bigger one, or you can have this destructive interference, which is where one is up and one is down and they cancel out. Then, of course, you can have anything in between. You can have a partial cancellation with wave. Wow, 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 wow. The really dramatic things and the way you can tell a wave is that you could never conceivably imagine two particles coming together and then for one instant in time completely disappear from the universe and reappear and continue on their way. Again, the really dramatic things and the way you can tell a wave is that you could never conceivably imagine two particles coming together and then for one instant in time completely disappear from the universe and reappear and continue on their way. It just doesn't happen. This is going to be our defining character of what makes a wave a wave. And when we are thinking about things like electricity and magnetism or sound waves or other kind of waves, we are going to look for this destructive interference. That's going to be our signal that we have waves. Wow, 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 wow. So that is going to be our signal that we have waves. Again, this is going to be our defining character of what makes a wave a wave. And when we are thinking about things like electricity and magnetism or sound waves or other kind of waves, we are going to look for the destructive interference. We are going to look for this destructive interference. That's going to be our signal that we have waves. Because this is a characteristic of the wave, that having a disturbance, destructive interference. Wow, wow. To summarize, we talked in the abstract way about waves and simple harmonic motion today. It's just a description of the nature. It's a very, very common motion. Every atom in your body behaves this way. Wow, wow, wow. When you drive the speaker heads move back and forth and then your eardrums moves back and forth. Then when you look at me, your eyeballs have electrons in the retina that jiggle back and forth. No matter where you look and no matter what you think about in nature, you start noticing oscillatory motion. It's obviously important to describe it, and it turns out that physicists love this because the The sine function is such a relatively easy mathematical description that applies to all of these different things. So it's obviously important to describe it, and it turns out that physicists love this because the sine function is such a relatively easy mathematical description that applies to all of these different things. It's easy to manipulate them, it's easy to understand them, and we'll continue on story next time as we talk about some more specific examples of waves. Thank you!